In this example, we want to write equations from which we can find the current I, positive in this direction, for this circuit using nodal equations two different ways. The first approach will be to use supernodes. As always, the first step is to define nodes. The reference node is entirely arbitrary. I'm going to choose it to be down here. So that's going to be 0 volts. I'm using supernodes, so I have to define dependent nodes. This 3 volt source will create dependent nodes. So this voltage and the reference voltage will be dependent on one another. The reference voltage is already defined, so this voltage is the voltage down here plus 3 volts. This is the positive terminal, so 0 plus 3 volts is just 3 volts. The 6 volt voltage source will also create dependent nodes, so this node over here is dependent on this node here. I arbitrarily choose one of those as my independent node. I'll call this V sub B. If this is V sub B, this node is 6 volts higher than this. This is the positive terminal, so this is V sub B plus 6 volts. Finally, I have one other node. It's independent. I'll call this V sub A. Now I'm going to do KCL at my independent nodes. So at node A, I'll always assume that positive currents are leaving. This current through the 3 ohm resistor going positive out of node A assumes this voltage polarity. So this current is V sub A minus V sub B plus 6 over 3 ohms. The current leaving node A through the 10 ohm resistor has this voltage polarity. So this current is V sub A minus V sub B over 10 ohms. And finally, this current source is putting 4 amps into the node. Since positive currents are leaving, this will be a negative 4 amp contribution. Those are all the currents at that node, so those sum to 0. Our only other independent node is this supernode B. So KCL at B. Again, I'll assume positive currents are leaving. Over here, this current is V sub B plus 6 minus 3 volts over 2 ohms, plus this current, which is V sub B plus 6 minus 0 over 7 ohms, plus this current, which is V sub B plus 6 minus V sub A over 3 ohms. Now let's go over to this side of the supernode. This current is V sub B minus 0 over 5 ohms. And this current through the 10 ohm resistor leaving node B is V sub B minus V sub A over 10 ohms. That's finally all of my currents. I can add those up and get 0 out of that. Notice that when I'm defining my currents leaving node A, I'm not worried about this current. I don't need to stick with that definition. I'm just going to assume that they're all leaving and worry about the current I later on. Speaking of which, I now need an equation to find I from the node voltages. So I is positive in this direction, so this is the positive terminal down here at the reference, minus the negative terminal. Positive current always enters the positive voltage terminal. So this is 0 volts minus V sub B over 5 ohms. Those are 3 equations and 3 unknowns that I can use to find I. Now I'm going to redo this problem without using supernodes. I still want to find a set of equations from which I can find I, but I'm not going to take advantage of dependent nodes. I still have to assign my nodes though. First, I choose a reference node. This is arbitrary, but I'm going to choose it to be the same choice that I did in the last time I did this example. So this is 0 volts. Now I'm not going to take advantage of the fact that I know the voltages relative to one another across these voltage sources. I'm just going to assign every other node in this circuit as being independent. So I'll call this node A, this will be node B, this will be node C, and finally this will be node D. Now when I do KCL at A, I can write the currents through the resistors according to the node voltages, but I don't know anything about the current through the voltage source. So I need to define that as an unknown. I'll arbitrarily call that I1. I'm choosing both the direction and the voltage variable arbitrarily. I also need to do the same thing for the 6 volt source. I'll call this I2. Now I'm going to do KCL at all of the independent nodes. I'll assume that positive currents are leaving the node. That choice is always arbitrary and can be changed at any given node, but there's no real reason to do that. So at node A, the current through the 2 ohm resistor is VA minus VB over 2 ohms. And the current through the source is an unknown I1. It's also leaving, so it's a positive term. Those sum to 0. Now let's do KCL at B. The current leaving B through the 2 ohm resistor is VB minus VA over 2 ohms. The current leaving VB through the 7 ohm resistor is VB minus 0 volts over 7 ohms. The current going through the 6 volt resistor is unknown, and it's been assigned as I2, and it is leaving node B, so that's a positive contribution, plus I2. And then the current through the 3 ohm resistor is VB minus VD over 3 ohms. Those are finally all the currents at that node, so that sums to 0. At node C, over here, we sum currents leaving the node. I2 is entering, so the current through the 6 volt source leaving node C is negative I2. The current through the 5 ohm resistor, positive leaving, is VC minus 0 over 5 ohms. And finally, the current through the 10 ohm resistor towards node D is VC minus VD over 10 ohms. Those sum to 0. Finally, at node D, the current through the 3 ohm resistor is VD minus VB, again assuming positive current is leaving the node, over 3 ohms, plus the current in this direction through the 10 ohm resistor is VD minus VC over 10 ohms. And we have 4 amps entering the node because of this current source. Entering the node will be negative, so that's a negative 4 amp contribution. Those sum to 0. Now we have 4 equations, but we have 6 unknowns. We've introduced these 2 variables, I1 and I2. We need to write 2 additional equations there. Those are called constraint equations. The constraints are induced by the voltage sources. So for this 3 volt source, we know that the voltage at this terminal is 3 volts higher than the voltage at this terminal. That means that VA is 3 volts higher than 0, so VA equals 3 volts. Also, the 6 volt source, we know that this voltage is 6 volts higher than this voltage. So VB is 6 volts higher than VC. This could also just as easily be written as VC is 6 volts lower than VB. That gives us 6 equations and 6 unknowns that we can use to solve for the node voltages. Now, once we've got the node voltages, we can write an equation for I. I is positive in this direction, so I is going to be 0 volts minus VC over 5 ohms. So without using supernodes, I ended up with 7 equations and 7 unknowns. Previously, when I did this problem with supernodes, I ended up with 3 equations and 3 unknowns. Each voltage source causes 2 additional unknowns. An additional unknown voltage and an unknown current. The 2 voltage sources in this problem created 4 additional unknowns. We needed 4 additional equations.